In my previous lecture on Newton's Principia, which is from a student's guide, chapter 19, I began going through the definitions of Newton. Specifically, we talked about his definition of quantity of matter. That's what we now call mass. We talked about quantity of motion, which is what we now call momentum. And we talked about his definition of vis insita, or inherent force, which is now, and he mentions this as well, called inertia. So let's start now with definition 4. So this is a continuation of Newton's Principia definitions. And we are on definition 4. So here he defines the impressed force. Impressed force or action. So we will typically just call this force. Oftentimes Newton just calls this action. And so what is an impressed force or an action? It is something that acts on a body so as to change its state of motion. Okay, so whenever you have an object or a body, remember by virtue of its inertia, it tends to retain its state of motion, whatever that is. So if it's at rest, it tends to stay at rest. And if it's in motion, it tends to stay in motion. But what happens when there is an impressed force or an action that is acting on that body? Well, its motion changes. One of the important things that he points out here is that the force, or this impressed force or action, and I guess we would just call this a force, the force is not carried along with the body, or carried along within the body. So it's not like when you apply a force to something and it begins moving, it's not like this force is sort of then subsumed into the body and is carried along with it. I'm guessing you might not have even considered this possibility, but a lot of people at the time were considering that possibility. They had this notion that when you apply a force to something, that force is sort of carried along with it, and then it can give up that force later on. That's not the way that Newton is thinking about this. Another thing that he points out is that there are many kinds of impressed force. So there are many, let me go back. There are many kinds of impressed force. So some examples of these are centripetal forces. He will spend quite a bit of time talking about centripetal force. So centripetal forces, magnetic forces, drag, so they're gravity. He's going to talk about these sorts of things. So those are some examples of impressed forces that attempt to change the state of motion of an object. Okay, let's go on to his next definition. So definition 5. Here, he defines a specific kind of impressed force or action, a centripetal force. So, what is a centripetal force? A centripetal force is an impressed force by which a body is drawn, he says, or impelled toward a point as to a center. So by which a body is drawn or impelled toward a point, says Newton, as to a center. Okay, so for example, maybe a simple example would be if you have your hand, let's say right here, and you have a string, and to the end of the string you attach a rock, and you spin this rock around over your head. So this is kind of looking down at you from above as this rock is spinning around. And at any particular moment, so this is the velocity at this particular moment, you know, a little while later when the rock gets over to here, then its velocity is going to be going that way, and so on. So this is a kind of two snapshots of a rock going around a center. What's happening here is the string is applying a centripetal force that acts inward. This is the centripetal force. The string is pulling the rock inward toward this point, which is the center. So over here, once again, we have the centripetal force applied by the string. It's always pointing toward that point as to a center. Okay? In the absence, by the way, of this centripetal force, this body, this rock, let's say, for example, if we were to suddenly cut the string when the rock is right here, what would happen? Well, the rock would then continue to move just in a straight line in the direction that its velocity is at that moment. So it would kind of fly off in this direction if we were to cut the string. And if we waited until it got around to here and then we cut the string, well, in that case, the rock would just kind of fly off in this direction, right? So it would continue in a straight line tangent to the circle, but the centripetal force is preventing it from flying in this straight line. It's keeping it moving in this circular orbit. It's important to recognize at this point that a centripetal force need not, so a centripetal force need not be a pull. It could be a push. Okay, so for example, let's suppose that you have, once again, I'm going to consider a top view. Let's suppose you have a hockey puck and it's sliding along in a straight line. Okay, so this is kind of the line along which it's moving. So it went from here to here. And let's suppose when you get right here, you hit it with a hockey stick. You hit it on this side. So you hit it with the hockey stick on this side and you cause it to deflect. Okay, so at that moment, you apply a force, a momentary force in that direction toward this point. Well, what happens is that this hockey puck then deflects, and now instead of going in this direction, now it goes in this direction, okay? So its trajectory was from here to here. As a result of that force, this is a centripetal force because it's acting toward this point right here, and now the hockey puck goes in that direction. Let's suppose now as it's sliding along here, somebody else standing there with a hockey stick strikes the puck and applies a force once again in that direction. Well, what's going to happen is this puck is going to deflect once again. So it would have kept going off in this direction, but as a result of this centripetal force that's acting toward this point, now it goes in this direction right here. And then let's suppose that when it gets over to here, once again, there's someone standing there and they hit it on this side with a stick. And so there's now a force acting in that direction. So whereas the hockey puck would have kept sliding in this direction, now because of that strike, now it's moving in that direction. Okay? So because all three of these forces are directed toward a point as toward a center, those can all be considered centripetal forces. So I guess the point I'm making here is a centripetal force doesn't have to be a pull by a string, and it doesn't even have to be continuously applied. Like in this case, the string is continuously applying an inward force. Here you have three separate discrete forces being applied to that puck as it's moving along, deflecting it, and the forces are being applied toward a center point. Okay, maybe I should make one other comment here, is that the force, centripetal force, could be caused not by physical contact. So for example, in these two cases, you've got a string pulling on the rock over here, or you've got a hockey stick hitting it, so they're in physical contact with the rock. But you might imagine if you can have centripetal forces that are not caused by contact, like if you have a magnet, let's say a magnet is flying or sliding along the ice, and suddenly you bring a magnet near it and deflect it toward a central point. You don't even need to touch it. You could just have this magnetic force acting on it, and that would be the centripetal force. Okay, and let me say one other thing before I move on from centripetal force, is that Newton, in this section where he defines centripetal force, is he gives a preview of where he is going, specifically his development of his law of gravity. He hasn't developed it yet, but there's a little bit of a foreshadowing here as to where he's going. And this is an interesting story that he tells, so I'd like to spend a minute talking about this. Let's suppose he considers the case where you have the Earth. So I'm going to draw a circle representing the Earth. And he says, what if you have a tall mountain? I know this is a bit of an exaggeration here, but what if you have a tall mountain and you have a cannon on top of this mountain? And you shoot a cannonball out of this cannon. And as we all know from studying Galileo, when you shoot this cannonball, it will follow a parabolic trajectory and it will land on the surface of the Earth. Okay, but here's where Newton has an interesting thought. He says, what if you were to shoot this farther, and you shoot it farther, and as it's falling, well, the Earth is kind of curved, so it's going to go a little bit farther, and the path is not going to be exactly parabolic anymore. And let's suppose you shoot it even farther, and so it's falling and it gets really far, and then it hits the Earth over here. But if you shoot it at just the right speed, as it is falling, the Earth is curving away from it the whole time, and so it never would hit the Earth, and it would come all the way around like this. So during this entire time, this cannonball is falling toward the Earth, but by virtue of the fact that the Earth is curved, it never actually hits the Earth. And so what would happen is this cannonball, let me get rid of these to get them out of the way. The cannonball, if shot horizontally with enough speed, would always be falling, but would never strike the Earth. It would be in orbit, so the cannonball would orbit the Earth. This is quite an interesting insight that he has, and you can probably see where he's going with this. What he's going to do is he's going to argue this is precisely what is happening with the moon. He's going to argue that the moon is falling toward the Earth, but it's moving with sufficient speed that it just never hits the Earth. And so this is really a precursor to the development of his law of gravity. This is just an interesting thought. If you think about this, you know, the astronauts that are on the International Space Station, they are doing precisely this. The space station is flying at an extraordinarily high speed, but it is falling toward the Earth the entire time. But because it's moving fast enough, it never hits the Earth. So you know that feeling when you jump off a high dive at the swimming pool, that feeling in your stomach as you're falling? Well, that's what the astronauts feel like all the time, because they are literally falling the entire time they're on the space station. They simply never hit the Earth. They are orbiting the Earth.